This is Steve Saltwick, and welcome to Your Brain a Personal Tour Seminar 5, The Neurogenesis of Human Culture. Today we talk about the human brain in all its glory. The goal of the seminar will be to investigate and present the unique capabilities of the human brain that give rise to the vibrant culture around us. We'll see that the truly unique aspects of the human brain are few in number, just 3 capabilities in my opinion. Over thousands of generations, each one of these 3 capabilities had tremendous power to bring about the culture we experience today. These capabilities built upon the non-human primate brain capabilities we covered in the previous seminar. The subtitle is about the skill of teaching, and it's an intriguing aspect on the human brain and human culture. Teaching and pedagogy are underappreciated aspects of neuropsychological research. We'll see that they had significant influence on our brain and the culture it developed, which is a wonderful way to begin this seminar. Welcome. I hope you enjoy the seminar. For those of you that enjoy the opening sequence, I present a roster of the images and their attributions for your reference. I challenge you to think about the images you would place on your personal slide of human culture. It's a fascinating exercise, and I encourage you to try it. One of those 3 unique human capabilities was seen in our opening sequence. It involves the typical reaction to the film of these triangles. As far back as 1944, researchers found that they could evoke mental state attribution when viewers watched a silent animation of very simple shapes like triangles or circles. Let's take a look at this one. In this film, I see a mother triangle, the large red one, trying to convince her child triangle, the little black one, to leave the nest. The mother coaxes her child out. The child is fearful of leaving the nest and must be kind of herded out. In fact, at one point, prevented from coming back in. Then, once fully outside, the mother and child experience the joy of playing outside the nest. Is that what you saw? Now, I want you to think about this. We were watching 2 triangles. Your brain was projecting intention and emotion on lifeless but cute geometric forms. This is called mentalizing, and it's thought to be a key, unique human trait. Your dog or cat does not do this. You may do it to your dog, but your dog doesn't do it back. As we shall see shortly, this trait sets up a massive amount of human cultural evolution. But let's introduce the other 2 human unique capabilities first. Here we see the 3 capabilities that I assert are unique to the human brain. 1. Mentalizing. We've just talked about that. It's what your mind did to those triangles. It's part of a repertoire called theory of mind or perspective taking. Your brain devotes significant resources in thinking about other brains' thinkings or feelings. This broad set of capability is termed theory of mind. We may call it TOM for short. In the middle, language is the second capability. Yes, Alex the parrot could talk, and several primates can use sign language, but no other set of brains on this planet is so wired for language as the human brain. Human infants show amazing capabilities and behaviors that far outstrip any other species. And then third, natural pedagogy is human communication and theory of mind specifically adapted for the efficient transmission of cultural knowledge among a generation and across generations. Knowledge that would almost be impossible to learn by imitation alone can then be passed using pedagogy from one generation to the next, so that the ever-expanding corpus of human knowledge can accumulate across thousands of generations and hence give us medicine, airplanes, iPhones, and unfortunately, telemarketing calls. In my reading of the literature, these 3 capabilities are the essential set of human unique traits which sets us apart from all the other species. But don't forget, the human brain builds upon the expanded capabilities of the brains of our non-human primate ancestors. We covered those in Seminar 4. There were 4 of them: a multisensory evaluation of future outcomes, the learning of abstract categories, focused attention on a goal that was several steps removed, and strategies to deal with success and the unexpected. The human culture we experience today is a combination of the unique capabilities of our human brains and the foundational capabilities of our non-human primate ancestors. Let's take a look at theory of mind in more detail. The theory of mind capability of your brain is also called mentalizing or perspective taking. And to better understand it, we're going to use an example. Think about a situation, perhaps in an earlier stage of your life. You go to the laundromat to wash your clothes, and one day you go into the laundromat and you see this. A stranger taking your clothes out of the dryer. With only a few seconds of perceptual data about this stranger, a typical brain will mentalize. Maybe she's going to steal my clothes. Or maybe she's feeling amazingly generous and she just does this as a random act of kindness. Or maybe she falsely thinks the clothes are hers. This native capability to reason about other people's actions in terms of mental states, their thoughts, their beliefs, their desires, emotions, and intentions is called a theory of mind. This capability is not present in the newborn brain. It develops. Using a test called the false belief test, otherwise known as the Sally-Ann test, researchers can show that a typical human child develops the capability for a theory of mind around the age of 4. A false belief test probes whether the child can represent in their brain a false belief held in another brain, imaginary or real. Let's take a look at 2 examples. The first will be from a 3-year-old undergoing this false belief test, and then the second will be a 5-year-old. Note the differences.
Yes!
This is Sally, and this is Anne. All right? Now, Sally comes in with her marble. Sally puts her marble into the basket and goes out. Anne comes and gets the marble, and she puts the marble in the box. Here comes Sally. Here comes Sally. Now, where will Sally look for the marble?
There you go, Sally.
You got it for her! Hooray!
The ball in the box. Can you open the box for me? Can you close it? Joey decides to go outside. And then May takes the ball and she puts it in the basket. And then Joey comes back inside. And where do you think he'll look for the ball?
In here.
In there. Why will he look in there?
Because that's where I put the ball.
And where is it really?
On the basis of this test, it's clear that a 5-year-old human brain can understand the situation where a different brain, yes, an imaginary brain, but a different brain nonetheless, can have a false belief. This is a consistent result. It's shown in both rural children and urban children. It has been found in Peru, India, Samosa, Thailand. It has even been found in hunter-gatherer children in Cameroon. There are differences in acquisition. Children presenting autism spectrum disorder show significant delays in the acquisition of this capability, and we'll discuss that later in the following seminar. Do non-human primates have a theory of mind? David Premack, a legendary researcher on primate learning, and Doug Gillen, a UT graduate, reported one example of a theory of mind experiment in the famous chimp Sarah, shown here at age 50. However, in the vast majority of past experiments, results show that non-human primates and other animals just do not have the capability as shown on the video. But, as are many things in science, it's not quite that simple. Recent research from 2016 onwards have shown tantalizing results for a theory of mind capability in non-human primates. These results have caused quite a stir in the research community. However, most results depended on measuring anticipatory looking, that is to say, measuring where and how long monkeys looked at an experimental situation. We can't ask the monkey about what some other monkey is thinking, so we measure where he's looking. And when we do this, we get mixed results. Since this is my tour, you're going to get my story on how to interpret these results. I believe that the body of research tells us a theory of mind is a composite of at least 2 levels of perspective taking. Non-human primates and some other animals have what is termed level 1 perspective taking. Humans are the only animals today that show level 2 perspective taking. What's the difference? Well, let's see. Level 1 perspective taking is building a common view of space for 2 animals. Here, a woman sits behind the far side of a blind. To her left, there's a chicken in plain view, but behind the blind is a kitten. The blind blocks her view of the kitten. An observer who has level 1 perspective ability is shown in the Sherlock Holmes suit on the right. He can correctly deduce that the women can see the chicken but not see the kitten, even though he can see the kitten. You might think this is obvious, but 2 to 3-year-old children often lack level 1 ability. To show level 2 perspective taking, we have to set up a thought experiment. This experiment will synthesize all the research I've read on the topic. It may be make-believe, but it represents the clearest view I have as of today. I need to introduce 2 participants in the experiment. Kaylee, one of our dogs, is the first participant, and you need to know she loves treats. Wiggin, another one of our dogs, is the second participant, and you need to know Wiggin loves toys, much more than treats. Here's our experiment on level 2 perspective taking. Our participant will predict what will Wiggin choose, toys or treats. One participant will be Kaylee, and for this experiment only, we will grant her the ability to talk. The other participant will be Becky, my wife. Okay, what does Kaylee predict? Kaylee goes, I love treats, therefore all dogs love treats, therefore Wiggin will choose a treat. Becky predicts Wiggin will choose a toy, since she knows Wiggin loves toys. What does Wiggin pick? The toy. Becky was able to see the choice like Wiggin sees the choice. She got inside his head and imagined thinking like he thought. That is level 2 perspective taking, walking a mile in their shoes, or paws in this case. Note that Kaylee believes all dogs think like her, and many do. But Kaylee just can't think about another dog thinking differently than her. Being able to think about someone else's perspective has massive impact on human culture. Some big ones: cooperative hunting. Early humans could coordinate their hunting. If you knew your hunting pal had the best shot to take down a prey, then you could assist by driving the animal to the best place for him to kill it. If you could imagine how a village boy was thinking about a problem, you could teach them more effectively. And if you could think about someone else thinking, well, you would realize that they could be thinking about you, and you would care what they were thinking about you. And voila, we have the grounds for reputation management. Theory of mind level 2 perspective taking is a major force in human culture and beautifully but densely described in the book A Natural History of Human Thinking by Michael Tomasello. If you're interested in this topic and don't mind technical language, then this is a book for you. If we scan the brain of a human being during the performance of a false belief task, we can see the activation of a specific brain circuit as shown here. I highlight one area in particular called the temporoparietal junction, or TPJ for short. Note, there's significant activity on both sides of the brain when we scan during a false belief test. This circuit is activated when your brain has to consider another brain's perspective or belief. It is not activated when your brain considers a false photograph, for example, a picture of a signpost pointing the wrong way. The effect is very robust and it's been replicated in many labs. Self-awareness and consciousness are major topics of brain research, and rightly so. A key question for the understanding of the brain is, how does consciousness arise? It's the hard problem of neuroscience and one that we must creep up on carefully. An intriguing result is that the recognition of your own face activates the theory of mind network. My interpretation of this effect is that one's brain is reflecting on itself as another brain. This kind of processing by your brain may be impactful in the construction of the conscious experience, for it's your brain being aware of itself. Perhaps we should rewrite René Descartes' famous expression, "I think, therefore I am," into a slightly more different formulation. I'm aware of my thoughts, therefore I'm human. More research on this is clearly needed, but it's a promising area of research into human consciousness. We've talked a great deal about scanning human brains, and I want to make sure we're aware of the power and the limitations of the tool. The machine we use is called a magnetic resonance imager, or MRI machine for short. An MRI machine can image virtually any soft tissue of the human body. When we want to study the brain, we use a technique of MRI called functional MRI, or fMRI. This technique, we measure changes in energy metabolism, or blood flow, to indicate brain activation. This machine is rather daunting. It makes loud noises as it generates magnetic fields in order to measure blood flow. If you've never experienced one, it can be quite unsettling, and I have some sounds to illustrate. Even with earplugs, the noises can be quite loud. Your skull is inside the donut, and it can be quite claustrophobic. Therefore, there's a running joke in the neuropsychology area that whenever you study fMRI, you can get artifacts, as in this cartoon, showing artifacts from performing an MRI during a memory task. Net, fMRIs can have artifacts, and we need to take those into account. The other big caveat that we need to be aware of with fMRI is that fMRI is correlation. Correlation is a mathematical measure of how two things vary together over time. It's a very useful measure in most studies. But just because two measurements vary together over time do not mean that one causes the other. Billy on the left is upset because every time the seatbelt sign comes on, the airplane ride gets bumpy. The graph on the right shows a highly correlated set of measurements. The first, the films of Nicolas Cage, and the second, the number of people who drowned in a pool. One of the important rules of this area of study is that correlation is not necessarily causation. Nicolas Cage films are not causing people to drown, and not turning on the seatbelt sign wouldn't stop the airplane turbulence. We just need to be aware of this as we look at correlational studies using fMRI. Theories about what is causing one variable to change with another are bolstered if we can get multiple types of data, say fMRI, data from stimulation, data from deactivation, etc., to show the same or similar effects. Don't get me wrong, fMRI is a powerful tool. We just need to be aware of its limitations as we look at the human brain. With these caveats in mind, let's return to our analysis about your brain and a theory of mind. Thinking about the thoughts show increased activity in the area of your brain called the TPJ region. But being careful of correlation, are there other data that implicate the TPJ region with thinking about thoughts, especially of another person? Well, yes, there are. The tool we're going to use is called transcranial direct stimulation. It is unique in that it allows us to either excite or depress certain areas of the brain without opening the skull. We're going to construct stories that can have different situations of belief for an actor. In other words, these beliefs can cause different kinds of outcomes. We show on the bottom left all potential threads of a given story. This is not the story that someone would hear. It is the set of all possible threads that could be presented. The story is about a customer in a restaurant who is allergic to sesame seeds. Kate, the server, is either aware of the customer's allergy or not. She serves the customer, and the customer either dies or does not from the seeds. Here are all the possible outcomes. If Kate knew about the allergy, served him seeds, and the customer died, then Kate has done intentional harm and should be held fully accountable for the customer's death. If she did not know about the allergy, then she did accidental harm, and her degree of blame or accountability is determined to be lower. If we stimulate the TPJ area of the brain while a subject is considering the blame of Kate in the accidental harm situation, the subject is much less likely to blame Kate, even if they were to blame Kate when the TPJ was not being stimulated. A closely related capability that we do share with many, but not all animals, is the expression of empathy. Mother Nature has endowed many of our relatives with this social emotion, including primates, elephants, canines or dogs and wolves, but even certain species of birds, like ravens and magpies, and some rodents, like the prairie voles we see here. As it turns out, there is a separate neural circuit for this capability, different from the theory of mind circuit just shown, and I want to explore that next. Empathy is the ability to share the feelings of another brain. If you scan the brain of a subject who is directly experiencing some kind of pain sensation and compare that scan to one where the subject is observing someone else in pain, you will find certain high-level brain areas in common. They're shown here on the scan in orange. This means that empathy truly is a vicarious experience. As Bill Clinton said, you really do feel their pain, at least at a high cortical level. This circuit is separate from the theory of mind network, but there are complications and overlaps. If you test for empathy as shown on the lower right, which involves a married couple, one in the brain scanner, one outside, and you cue for pain in the abstract, for example, using arrows, your brain activity shows activity in the empathy circuit and the theory of mind network. But if you cue with a concrete cue, like, for example, a prick of the hand or a stubbing of the toe, then the theory of mind network is not active. The empathy circuit and the mirror network are active. We covered the mirror network in Seminar 2. It's as if the motor act is being analyzed for its intention and planning is active for how to avoid this particularly painful stimulus. So empathy is a complex, multidimensional process in your brain, and it can be modulated by surprising events. One of the most intriguing modulators of the empathy circuit is social. Let's take a study of one part of that circuit at a place called the anterior insula, shown by the red circle in this scan. We're going to do two things. First, we're going to have subjects play an economic game with either a fair or unfair research assistant before the brain scan. We then scan their brains as we apply pain to the research assistant. At least that's what the subject believes. Females are highly empathetic, and that's shown with the purple bars on the top half of this diagram. Females are less empathetic for the unfair player, but males are positively revengeful for the unfair player. Males have no empathy for an unfair player. In fact, they want to punish them. Alternately, we could measure empathy when the subject is either within or without a group. In this instance, we study males where the membership in the in-group means that the subject and the research assistant are rooting for the same soccer or football team. Being a member of the out-group means rooting for a different soccer team. You can see that males are much more empathetic to members of their own group compared to members of an out-group. This effect is very consistent. It also applies to females in different situations and can be called an us versus them effect. Us versus them effects are present in a wide variety of animals, including humans, and they bring about some very strange aspects to behavior. A wonderful story about one of those strange effects occurred on the set of the Hollywood movie Planet of the Apes. I'm old enough to remember well this movie. If you're not, hit the Google button. Actors had to eat lunch in their makeup as shown here, but there was a fascinating aspect to lunch. Actors representing chimps ate together. Actors representing gorillas ate together, and the same with the orangutans. There was no rule about doing this, they just did it spontaneously. The us of the chimps didn't want to eat lunch with the them of gorillas. Oh no! In all likelihood, the actors were not all primate racist, so what's going on? Well, it turns out that your brain has an ancient fundamental neural pathway devoted to the processing of us and them hallmarks. Let's look at a few of those next. To demonstrate that the neural pathways in your brain are fundamental, we can use reaction time experiments. In these experiments, an image is presented for about 1/10 of a second. The images are subliminal. The viewer is not certain that they've even really seen anything in particular. We measure the influence of the presented image on a subsequent task. And if there's an influence, we conclude that there was an unconscious impact on a brain process. What kind of aspects influence your brain with conscious knowledge? Well, gender and ethnicity and socioeconomic status and race. In each case, your brain is most sensitive to the dimension that is not you. In other words, if you're male, you react faster to female faces. If Asians, faster to non-Asians. African American, faster to Caucasian. Your brain instantly reacts to these dimensions via ancient pathways laid down by Mother Nature. From an evolutionary viewpoint, such reactions were clearly valuable. But in today's society, such reactions support the development of stereotypes and further the divide between us and them. Is there anything we can do to moderate this effect? Well, yes. And I want to use the automatic manual mode analogy again. I use a very effective ad campaign to capture the essence of the effect. Your brain has an automatic mode that quickly categorizes faces and other objects along an us, same as me, and them, different than me, dimension of gender, race, etc. In evolutionary times, this had survival benefit, and the brain pathways were conserved to the present day. The net effect is that these pathways support the development of stereotypes that can be counter to maximum productive societies. The way to break through is to bring in the deliberative mode in the areas of your brain and make the anonymous face a person. The more your brain considers a face a specific person with attributes your brain can relate to, and then the less you will get a stereotypical behavior. Note, your old brain pathways are still signaling us, them. The rest of your brain is overriding them with specific information that blocks or reduces stereotypical reactive behavior. And that's a good thing. And it's something we can all do. It's work, but it's worth it. Time now for Homer to join us and give us his thoughts. Homer is incredulous that everybody doesn't think like him. In other words, Homer is stuck in level 1 perspective taking. Thankfully, Homer was not the first human. Level 2 perspective taking, thinking about the thoughts of others, is a unique human skill as of today, and it underlies much of our culture. But ancient pathways useful for the emergence of human culture gave rise to stereotyping and other unhelpful behaviors. Thankfully, such behaviors can be overridden, but they are still there, but moderated by the perspective of other brain areas. Now let's turn our attention to the second unique aspect of human brains, the facility for language. No other species seem to be wired for language like humans, whether that's speech, gesture, or writing like the Mayan glyphs. Our brains are endowed with the spectrum of language skills that are clearly the apex of animal capability. Let's see what that means in more detail. Years ago, there was a simple story to the way your brain processes language. On the left side of your head, there were two areas that fundamentally process speech. Broca's area was responsible for how you said what you wanted to say, and Wernicke's area interpreted the speech you heard. Note the path between the two, which bypasses the vocal cords. That's the path for the inner voice in your head. Today, this diagram is still mostly valid, but we need to change the words related to speech and hearing to words associated with communication. Because Broca's area not only helps your brain figure out what to say out loud, it's also involved if you sign your speech, or even if you pantomime your speech. In this instance, let's open a jar. Broca's area seems to be a pattern generator for motor programs to communicate, either in speech, gesture, or pantomime. Likewise, Wernicke's area is not just about hearing words, but about reading words, or surprisingly, pantomiming words. In this instance, the phrase, "I've got it." This is a fascinating area of study right now. I want to emphasize that these language areas are not just about making the sounds of speech. They seem to be trying to communicate a thought via whatever motor program is most efficient or available in the communication path. In over 95% of the population, regardless of handedness, the majority of complex language processing is contained in the left hemisphere of your brain. We can use split brain patients to help us further understand how language is processed between the different halves of your brain. Split brain patients have had their brains transected as a function of the treatment of epilepsy or some other neurological condition. Also recall that the brain halves control the contralateral side of the body. The left side of your brain controls the right side of your body. The right side of your brain controls the left side of your body. With split brain patients, we can present separate pictures to each side of the brain and then query the subject for how they're processed. In one famous experiment shown here, a chicken foot was shown to the left half of the brain and a snow scene to the right. The patient was then asked to pick out appropriate pictures with each hand. Since the right hand is controlled by the left brain, a rooster head was selected. Likewise, a shovel was selected by the left hand. The subject, when asked why he picked the shovel, didn't mention the snow scene. His left language area was not aware of it. He replied that you need a shovel to clean out the chicken coop. The next panel shows that the right brain is not completely absent language skills. However, the right side skills are minimal. It cannot process complex grammar, but it can read words. Here, the patient correctly read the words presented to the right brain and correctly performed the behavior. However, the left brain did not have knowledge of the word presented to the right brain, and when the subject was asked why they were laughing or walking, the patient basically made up a story. The story subject was not surreal. It was a rational explanation of the behavior, just not grounded in facts. We'll use these insights in the next seminar to explain some psychological disorders. Theory of mind attributes offer an excellent foundation for the framework of language. In such a framework, language is a tool for transmitting one brain's mental state to another brain. Speech is probably the most effective modality, but gesture, pantomime, and writing can also be effective. If this framework is reasonable, then we should see a coupling or synchrony between a speaker's brain and a listener's brain when we scan the brains listening to a story. And guess what? That's exactly what we see. On the right side of this diagram, the area in blue depicts synchronization between a speaker's brain and a listener brain when a speaker relays a story. This synchrony is reflected in correlation of brain scans. Yes, correlation is not necessarily causation, so it's appropriate to ask if there are other compelling results that show a coupling between a speaker's brain and a listener's brain, and boy, oh boy, are they. In this experiment, there's one story. The story has been translated from English into Russian. There are two classes of listeners, native Russian speakers and native English speakers. The top part of the slide shows very little coupling between the brains of the two classes of listeners when just the Russian story is played. Coupling is shown in orange on the brain diagrams. However, if we play the story in Russian to the Russian speakers and we play the story in English to the English speaker, there is significant correlation between the brains as shown in orange. The brains are locking on the meaning of the storylines. You can see this same effect when people watch a movie together. The brains are synchronizing to the meaning of the story. Theory of mind circuits are active in language processing as the listener considers the mental state of the speaker. In this example, we scan the brains of a listener when they hear the phrase, "It's hard to give a good presentation." There's two preconditions. One, in the direct condition, the listener hears a simple direct question that requires no evaluation of the mental state of the speaker. Is it hard to give a good presentation? The answer is simple. It's hard to give a good presentation. It's a matter of fact. In the indirect case, the listener hears an ambiguous question, the meaning of which requires consideration of the mental state of the speaker. Theory of mind circuits, especially the right TPJ, are active only in the indirect situation. Listener brains are always evaluating the incoming communication for triggers to consider a speaker's mental state. This assists the listener's brain in coming into what is within the speaker's brain. Recent research has shown that there's an amazing similarity of the semantic maps between brains. In April 2016, researchers at the University of California, Berkeley published a dramatic map of the brain, a cartography of word meanings. I will play the video of this presentation in just a minute, but I want to emphasize the findings. The meaning of words, the semantics, are grouped in similar areas across different brains. These groupings imply a common framework of meaning, at least for the brains of Berkeley students. It'll be fascinating to see if this holds up across cultures different from Berkeley. And there just might be a lot of cultural differences between cultures and Berkeley.
This is a map of someone's brain, showing roughly which areas respond when they hear different words. For example, there's a small area in the middle frontal gyrus that reliably responds to hearing the word top. But it's not just one word, one location. A single word can activate a whole range of different brain regions. So we find the word top in a bit of brain that seems to respond to words associated with clothing and appearances. But also here with numbers and measurements. And here with buildings and places. We usually think of language as being restricted to certain sections, like the temporal lobe. So researchers were surprised to find activity all across the brain and in both hemispheres. The map was made by scientists at the University of California, Berkeley. They put volunteers in an MRI scanner and had them listen to stories for 2 hours.
Back in the front again, deep, deep, and she pulls out a pack of matches that have been laundered at least once.
By monitoring blood flow to different parts of the brain, they worked out which places were responding to the meaning of the words, the semantics. They found that different bits of the brain responded to different kinds of words and concepts. And they could group them into rough categories, shown here by the different colours. Dark green bits, for example, were most activated by words to do with numbers, red bits by social words. Here in the right temporoparietal junction, this speck of brain, just a few millimetres across, was found to respond to words like wife, mother, pregnant and family. And this bit just next door responds to some of the same social words like family and wife, but also words to do with places and people like house and owner. Generally, the concepts represented in each brain region relate to other functions that scientists already know about. So words to do with how things look, such as stripes, are likely to be found near the visual cortex. And although each individual's map is different, looking at these 3 brains, it's clear that different people have the same kinds of concepts in the same kinds of places. This is the first time we've been able to map the semantic systems of the brain in such detail, discovering that words are grouped by meaning, and revealing just how complicated and widespread the word maps in our heads really are. And the brain map is available online for anyone to explore.
I draw your attention to the fact that there is great similarity between brains of different people as to where the meaning of a particular word is stored. Yes, each individual is different, but there's a surprising and significant congruence among the brains tested. So, since different people seem to store the meaning of a word in roughly the same place, we can use that fact to implement brain decoders to help us glimpse some of the inner workings of the mind. Here we see the output of such a decoder when a subject is watching movie clips. The decoder displays the words and phrases active in the brain of the viewer. There is a time lag, and the decoder does not work well when the scene changes rapidly. That's because of the delay of measuring differences in blood flow. But I think you'll agree this kind of analysis is fascinating and, frankly, a little bit troubling. The use of this technology has also opened up possibilities that are not just frightening, but stupid. I show here a slide from the latest Facebook Developers Conference in 2017. Facebook wants to use brain decoders of information to allow you to tweet or send messages directly from your brain. You think it, you tweet it. That is a terrible idea. I leave the real-life parallels to the viewer's imagination. Of more importance and interest, I think, are the fields of study that are enabled by this kind of research. The holy grail of semantic research is how are words and concepts stored in the brain. This kind of research has progressed our understanding in ways that are surprising. For example, we now know in all likelihood that the diagram on this slide, which was the leading candidate of how meanings and concepts were stored, is not correct. A computer programmer would say this diagram is a great theory of meaning. A brain scientist now would not. This model of your brain held that there is a rigid hierarchy in how concepts are stored. Specific information was stored at the lowest level and more general information was stored at higher levels. A word or concept at one level of the graph would inherit all the properties of the elements above it. So, for example, a canary can specifically sing, as shown here, and since a canary is a bird, it can also fly. And similarly, since it's an animal, it can move. And since it's a living thing, it can grow. While elegant as a computer model, this is just not the way your brain does it. And, as you might guess, it's a bit more complicated and messy. Here is a diagram which I believe is much closer to the representation of words and concepts in your brain. Nouns are called items, verbs are called relations, and they're associated to attributes with connections, which in real life are neuron-to-neuron connections. Experience and learning, that is to say memory, can strengthen or weaken the connections over time with the mechanisms we studied in seminars 2 and 3. Let's take our example again. The combination of the item canary and a relation, can, is related through a mess of connections to the appropriate attributes: grow, move, fly, and sing. The connections have been learned over time. This kind of structure is much more helpful in explaining the behavior of patients with a type of stroke which is called semantic dementia. This model is also very helpful in understanding how a normal brain works. Let's see how. The model of semantics, or of meaning, that we have been exploring is expressed in the brain with what is termed a hub and spoke system in your temporal lobe, the part of your brain by your temporals. Of note is that each attribute of an item, that is a concept or a word, is individually expressed in the appropriate sensory or motor area of the brain and then collected into a multimodal hub at the end of your temporal lobe. This kind of model has been shown very successful at explaining brain operation, and I want to emphasize 2 major points. First, the meaning of a word or concept is multimodal. It has aspects of sight, sound, and the other senses, but also has aspects of how it is used, function, how it is gripped, praxis, how it is pronounced, etc. This is a critical insight from the model in semantic memory. Second, the hub receives all this information representing the concept as the sum of all factors. This concept corresponds well to how the brain works normally, and when the hub is damaged, the patient may lose the memory of how to handle it, i.e. lose praxis, but still knows what it is when they look at it, or vice versa. These are exactly the symptoms we see. Let me illustrate this model of the brain in operation. The hub and spoke network of the temporal lobe represents objects in a multimodal way with some kind of default organization. Here we see objects categorized like we may have learned them in school. Birds together, fish together, flowers together, and trees together. The function of this network in your brain is to represent objects, and it does that across all sense modalities as well as many other dimensions. For example, type of motion. Now, if we give you, that means your brain, a task to do, let's say sort those objects by the type of motion they have or by their color, we see a different area of the brain get involved, the prefrontal cortex. That part of your brain is the control network. It represents the task or the rule to use. We show the two tasks here, selection for the type of motion and selection for the type of color. This is amazing. It's a real window on how humans think, and there will be much exciting research coming in the near term. It's time for Homer to weigh in. Homer's 2 points are as follows. First, consider language a tool to transmit mental states from one brain to another. This is a theory of mind framework, which has great utility in understanding our brain. Second, semantics, or the meanings of words, in normal brains seem to be stored in standard locations, at least amongst the brains sampled so far. Note that they're all in the same culture so far, so more experiments are needed, and it'll be extremely interesting to see the results from varying culture or from different kinds of psychological dysfunction. Let's now explore the third human-unique capability. There's a large body of research which concludes that humans are the only species which as a whole utilize a communication framework allowing and facilitating the transfer of knowledge to novices, not just family members, but widespread members of tribes or larger social groups. We'll call this framework natural pedagogy, and we'll introduce its key characteristics in this, our last section. Those key characteristics are: 1. Infants are wired to learn from birth onward. 2. Theory of mind, language, and mirror circuitry in the human brain makes it possible to mirror the intent of a demonstrator, for example, to manufacture tools. And 3. The rewarding effect of being understood enabled a positive feedback cycle of pedagogy. This pedagogy cycle gave humans an evolutionary advantage, which over thousands of generations resulted in the culture we see today. This is a new area of research, and I think it offers stunning insights into human culture. The first capability shown by human infants for supporting pedagogy is sensitivity to what is termed ostensive gestures. This capability is present at 4 months of age and might even be present earlier. Ostensive gestures are gestures that signify intentional communication. A good example is direct eye contact or a raised eyebrow. Human infants are very sensitive to these gestures, as shown on this slide. The top tracing is an EEG brain scan of a 4-month-old infant under 2 conditions. The top row is the infant seeing a face with a diverted gaze, which then raises an eyebrow and smiles. As you can see, there's no significant EEG or brain activation. In the bottom row, it shows the reaction of an infant to the same eyebrow raise and smile, but this time the face is directly gazing at the infant. Both gestures significantly affect the EEG. Similar effects have been shown for other primary ostensive gestures, motherese or baby talk. Net, the infant is barely out of the womb, but it's very much in tune with efforts to communicate with them. So, look directly at your infant grandkids and smile. Coo, talk baby talk. Tell your kids that science says it's all okay. By 6 months of age, an infant is reliably using ostensive gestures to initiate gaze following. In this example, an experimenter uses eye contact on the top row, or motherese baby talk on the bottom row, to signal an imminent communication, a direct gaze at one of 2 toys. If there is an ostensive gesture, eye contact or motherese hello, then the infant reliably follows the gaze towards the ball. If there's no ostensive gesture, no eye contact, or no infant-directed greeting, then there is not gaze following. To ensure that the looking of the infant was equivalent between the two instances, a colorful cartoon was placed on the head of the experimenter. The flower-looking symbol you see on top of the experimenter's head is to ensure the infant didn't turn and orient towards the experimenter, and that the situation was similar between eye contact and no contact. By 9 months of age, the infant has mastered the distinction between an ostensive pointing movement and a simple reaching for an object. In this experiment, the infant observes an experimenter either reaching for an object or pointing to an object. Following this, the infant's view is blocked for 5 seconds, during which time the object is either moved to a different place or changed to a different object. Then the screen is removed and the infant is allowed to observe again. In the reaching situation, the infant will notice a change in position, but not a change in the object itself. The interpretation here is that the infant understood the intention of the motor act of reaching, but it did not attach any importance to the object. In the pointing example, the infant was surprised and looked longer if the object was changed. The ostensive gesture of pointing signaled that the object was important, and therefore any change was significant. These capabilities set the stage for pedagogy. A good way to see the impact is to look at tool making in the Stone Age. This slide shows a simple stone cutting tool that was found in the historical record of about 2 million years ago. The tool is classified as an Oldowan tool and is very crude. It's made with flaking chips off a coarse stone with stripes from a hammerstone. Research in the lab has demonstrated that non-human primates like chimpanzees can create Oldowan tools merely by imitating the striking movements of the hammerstone as demonstrated by a human toolmaker. There's no need for ostensive gestures. There's no need for understanding the intention of the demonstrator. It's simply a matter of imitation. That was probably the state of play 2 million years ago. Between 2 million and 700,000 years ago, tool making evolved to the diagram you see on this slide. Two workers cooperate to work on a much more advanced stone cutting tool called an Acheulean blade. An example of the blade is shown on the top right. The blade is far more effective than previous Oldowan tools. It can be hafted, that is, attached to a pole or handle to form a very effective killing weapon. With such a weapon, larger prey could be killed and consumed. The important point here is that research has shown that merely imitating the motor act of a demonstrator will not produce a good tool. The intent of the toolmaker needs to be copied. A sharp edge to be fastened will vary from core stone to core stone. Imitation will simply not cut a good tool. When we scan the brains of people making such a tool, we see activity in the mirror system and in the prefrontal cortex. In previous seminars, we've seen that these are areas that your brain has to support goal-directed behavior and replication of the intent of a motor act. Now, at this stage of evolution, both workers have brains with a theory of mind and language. The intent of the tool making can be communicated with speech or gesture or pantomime. These acts are pedagogy. They give the tool makers evolutionary advantage over generations. But there's also an effect that works in real time between the tool makers. Let's look at that briefly. There is rewarding value to being understood. While this might seem obvious, we need to show it experimentally to confirm it as a driver of pedagogy. We'll show this by having students record a video clip in which they think will be reviewed by other students. When we scan their brains when they hear the reviews of video clips and watch the reaction. Researchers manipulated standard replies so that half of the reviews contained statements supportive of understanding of how the student felt. The other half of the reviews contained statements that indicated little or no understanding of how the student felt. Theory of mind circuits and the reward circuits were activated only in the being understood set of trials. Voila, the blatantly obvious, people like to be understood, now has neuronal research underpinnings. If you allow me rank speculation, consider the demonstrator in a tool-making situation 700,000 years ago. He, and it was a he, had the same brain as males do today. His theory of mind circuit is trying to communicate the intent of the goal for an advanced stone weapon. When information comes back to the demonstrator's brain that he's being understood, that's rewarding. Hence, he's likely to repeat such acts again and again and again. Not only does being understood make the demonstrator feel good, it drives a process of cultural transmission, and this could relate to stone tools, cooking recipes, or creation myths. Pedagogy, or teaching, sets up a system in which is the most reliable way to specifically transmit information across generations. The figure shows what happens over multiple generations of rug weavers in Central Asia. The pattern of a specific rug ornament was studied over these generations. The highest fidelity is shown in the teaching path. So for skills that are the most demanding, teaching, in other words, pedagogy, is the method that will culturally transmit the best information on a skill across generations. Scientific discussions are only just now considering the impacts of pedagogy. Imitation can explain much in the evolution of our species, but complex and difficult skills to master, making stone tools, pottery making, textile making, and cooking, require guidance and control of learning. Being wired to learn from birth by having brains that consider the perspectives of other brains and being rewarded from being understood, humans are wired for pedagogy. And pedagogy evolved for the betterment of the species, betterment of diet, betterment of longevity, and betterment of culture. It's time now for Homer to make his final appearance in this seminar. Homer has two simple points to make. First, humans are wired to learn. This is an essential element and driver of our evolution and culture. The second point is that pedagogy is truly a divine calling. It was and is essential to the positive development of human culture. Even though it may be used to take people to the dark side, its impacts are underappreciated in the research literature, both in terms of human neuropsychology and anthropology. Further scholarly research will be much appreciated in order to better understand this element of our evolution and culture. This concludes Seminar 5. I hope you enjoyed it. In Seminar 6, our final seminar, we'll talk about how the ecosystem of your brain can go wrong. From aging, from damage by stroke, from miswiring. I promise it won't be a downer, however. We'll also cover the most recent research on repair of function. There are many reasons to be excited about this area, and while admittedly there's still much to do. The subtitle of the seminar is Dog Walking and the Jedi Monkey. You'll have to wait on the Jedi Monkey bit, and you will be amazed at what dog walking can do to repair an aging brain. I look forward to you joining me again in Seminar 6. Thank you. This is Steve Saltwick.